Hello, sir. Thank you so much for taking the time to speak to me, and welcome to Tech Brew.
Well, pleasure is mine.
Sure, sir. So, let's start with the whole expert piece that you're on. Most people think of coal primarily as an energy resource, but you've been exploring a different perspective. In fact, one that looks at coal as a foundation for deep tech materials and future industries. So, tell me about what this idea is and why do you think it's worth paying attention to?
So, long time ago, when I was in Bell Labs, I was in Silicon World, information age. We were making chips from silicon. And I realized pretty fast that if you take pure silicon, it is really not very good for us, especially for making chips. We put some defect, we put some dopant into it so that it can become a semiconductor material. So it is that small amount of impurity that we add into silicon that makes it possible to be the fundamental chip for the information age. Without that impurity, we will not know what to do with it. And then I realized later on, my first project was how do you grow these silicon ingots from impure silicon? Okay, so we use the Czochralski process and we grow silicon ingot, which is about 2 meter tall
Okay.
and about 125 millimeter diameter when I was there. But then from the crucible, which is made out of silicon dioxide, it incorporates oxygen as an impurity into silicon. So what do you do with this impurity, right? So, well, we engineered it. We found a way. Number one, when we grow the crystal, the top part of the crystal has large amount of, the next part has little smaller, the next one, the last part of the crystal ingot, which is the 2 meter tall, that has even fewer elements of oxygen. So what did we do? We said, okay, we'll chop the ingot into different portions. Oh, this was this much oxygen, this has this much oxygen, this one has very low. So depending on the device, we will use it. Okay. But then we found a way of putting those impurities, this is important, putting those impurities into the crystal, into the silicon wafer, deep into them. They act as a gathering site. They then start getting all the impurities, like metal impurities, which are deadly for the silicon chip. So they act as impure gathering site, and they say, okay, we will collect all the impurities here. Okay, and then we say, okay, we won't use that portion of the wafer. We will only use top portion of the wafer, and we'll make our chips into that. So impurities became, for me, coming from Cornell, where our focus was really on abstract research. Okay, why does it happen anyway? For example, my PhD work was why does flow become turbulent from laminar to turbulent? So here the impurities, which we didn't tolerate back in abstract science, pure science, here impurities were the one which were allowing us to usher in the information age. So then when I came here to Virginia Tech, when I stepped down from my duties as the first or the founding executive director of ICTAS that he mentioned, I said, well, I really need to look into this new material called graphene. It is called the wonder material because it has absolutely pristine graphene. If you think about it, it is only 0.335 nanometer thick. It basically doesn't have a third dimension. It's so
Right.
small thick. And 1 nanometer, as you know, is billionth of a meter. And if you take single strand of hair, that is 200,000 to 300,000 times larger than what our this graphene chip,
Graphene.
single pristine graphene thickness is. So it is that I said, okay, so graphene is a pure material. But going back to my Bell Lab days, I said, but it is chemically inert. It doesn't have the impurities. So what if I take impurities and add them into this? Add them into the pristine graphene. Pristine graphene is very, number one, extremely expensive. It's $100 to $150 a gram. and it is made up by a process called chemical vapor deposition process. In that process is very expensive and it's not good for scaling it up. So people use a different method called Hummer's method. Okay? And the idea is we'll take graphite, pure graphite, and convert that into graphene. Okay? But that process, number one, graphite is available only from most of it from China. 100% of synthetic graphite comes from China, and 70% of mined graphite comes from China. So United States, here we were very worried about that, and I'm sure so are many other countries too. But graphite, pure graphite, it has a lot of graphitic layers, and they are bound by van der Waals forces. So you need high, really concentrated acids to separate those graphitic layers. So I said, wow, like it comes from the same Mother Nature. You have fossils, and Mother Nature converts at high temperature and pressure first into coal, and then there's a lignite, which is available in southern India, for example, converts into bituminous coal, which is available in Northeast, converts into anthracite available in Jammu and Kashmir, and
Interesting.
then to continue the process, it converts it into graphite, and then maybe into diamond. So basically, the starting material is the same.
Same.
And I
Correct.
said there are defects in each of those processes. Maybe I want to start with coal, and since it is not, graphitic planes are not so bound to each other, maybe I can get away with smaller amount of acid or only one acid, and maybe I can convert that into graphene, the so-called wonder material. And on top of that, depending on my precursor material, which is lignite or bituminous or semi-anthracite, I can have different defects in them, which mean they can be used for different applications. But the first thing is, can I convert that coal into graphene? And I talked to my research team and my chemist who was working with me. She said, within a week's time, she came and she said, yeah, I think I can use only one acid, nitric HNO3, nitric acid. And small amount of that, I don't have to use sulfuric acid. I don't have to use other difficult acids that we use with Hummer's method, which is the current standard method for converting graphite to graphene. If we take coal, which is a cheaper material, much cheaper material, and it has defects in it, and I can convert that into graphene by using very one simple acid. And then depending on the lignite, depending on the precursor, lignite versus bituminous versus anthracite, the amount of the concentration of acid, single acid that I use, that can be much different. For example, for semi-anthracite coal, for which I have a patent, we use 16 mole. That means 100% concentration of nitric acid. For bituminous, it is 75% concentration. For lignite, it's even better. Okay. So
Okay.
that means I already have a rich resource available in Mother Nature. And the same coal which is used for producing electricity or producing power and having also the pollution with it, I can now use the same coal for converting into graphene, the so-called next wonder material, which has beautiful, absolutely wonderful properties. If you take pristine graphene, it is, if you want to think about it, let's say mechanical engineering, right? Strength, mechanical strength. It is 100 times stronger than any material, most of the materials we know, steel, copper, aluminum, it is 100 times stronger than that. If you think of its thermal conductivity, it is the material known for highest thermal conductivity known to mankind, about 5,000 watt per meter Kelvin. And if you think copper, which we think is very conducting, we make our vessels out of it, right, for the cooking, because it conducts heat very nicely. So that's much lower than this. It's about 10 times smaller than this. So it has wonderful properties, and that's why it is called the next wonder material, because teeny mini small amounts of that, if we add to something, for example, if we take plastic or a polymer, and we add 1% by weight of this material, that becomes mechanically very strong. If
Okay.
we take polymer, which is a thermally insulating material, if I put small amount of this, I can use this as a thermal interface material between a chip and a heat sink so that the contact resistance is reduced. So it has lots of applications, and we have actually shown through a number of applications that graphene and its derivatives, like graphene oxide, for example, it has antibacterial properties. So lots of wonderful properties where we can go from graphite, which is not even, we don't mine it and we don't synthetically make it because of the environmental considerations. We import it. And same thing in India. Most of the graphite is imported. So the question then is, can we use coal, which is conventionally used as a resource for producing electricity or power
Energy.
generation?
Yeah.
Can we convert that into by a simple method? And depending on the region, South India, okay, we'll take lignite. Last thing I'll mention to you is impurities differ in lignite versus bituminous versus semi-anthracite. If I mentioned lignin earlier, that was a mistake. Lignite. So if you take lignite, for example, it has impurity by calcium. And it turns out calcium is a catalyst, which means if I want to convert coal into graphite instead of graphene,
It
because
is.
graphite has many other applications, electric vehicles and all that stuff. So then, maybe I should use lignite as my starting material because it already has calcium, which acts as a catalyst. Okay. So I can maybe convert it into graphite at a much lower temperature than 3300 degrees Celsius. So depending on the impurities available in different parts of India, with different kinds of coal, we can now come up with applications which are, hey, this one is very good for converting to graphite. This one is very good for antibiotic properties. This one is very good for converting it, putting it into polymers to make it mechanically strong. So I think this can be I call coal the next wonder material. So we can
Right.
convert it from growing into pollution and going power. We can now use it for making next generation of solar cells. We can,
Good.
so we can take any application where we use it, and I can say, okay, I'll take this and go to perovskites, or I can use graphene for such and such purpose, and I can now have a new economy. We can make our coal miners, we can make them into high-tech workers. They can take one application and say, okay, we are going to make the new masks, which will be the mask preventative thing against, say, COVID-19 virus or any other virus. Okay? So I think depending on that, we can make tiles, for example. The last thing I'll mention to you. We can make tiles and coat it with graphene oxide made out of coal. Okay? Graphene oxide, it kills E. coli. So
Okay.
imagine if we go into hospitals and the surgical room has tiles which are just simply coated with graphene oxide.
Hmm.
So that
Okay.
means coming out of it, most of the times in India, we go to hospitals, many a time, we get E. coli infection. That's not only in India, even here. Okay.
All right.
So now all I have to do is coat these things with graphene oxide and I'm done. Right.
Got it.
So a
Got it.
lot of applications that we can make.
Sure. So like you said, of course, the number of uses that you've just mentioned with graphene, just to bring the context back to say deep tech, manufacturing, semiconductor. I know you mentioned we can use it in the wafer. Can you just emphasize a bit more on how helpful it is in this whole process and which all industries would be the most benefited out of this?
Yeah, so one of the things that I have been working on right from day one, I'm a mechanical engineer with heat transfer background. And so looking at the thermal management of data centers, for example. Okay. So first, in answer to your question, first one is if you look at how the process of, if you look at the data centers, we are looking at very, very small devices. we are looking at 4 nanometer devices. We are talking about earlier 4 nanometer transistors, which are now used in a lot of the high power chips that we get from Taiwan. So if you have a 1 centimeter square chip and you have only 4 nanometer transistor, you are talking about billions of transistors on one chip. Now, if each one of them produces a teeny mini amount of heat, but it's pretty large amount of heat. So you can produce, if you think about it, 1 kilowatt per square centimeter from one centimeter square of a chip. You can produce 1 kilowatt of heat, right? So how the heck you take care of that heat? Because if the junction temperature goes up of a transistor, its reliability goes down. We cannot afford it to go above 105 degrees Celsius. Okay. So then we have so much amount of heat to remove, right? So, the question is, how can I use, number one, can at the back of the wafer, can I do something on the passive side of the wafer, not the active side of the wafer? Can I do something there so that I can remove that amount of heat? Because otherwise my devices will be hugely unreliable. Okay, I cannot use them for defense purposes, maybe for consumer applications. Okay, 1 year, it will last only 1 year. So, so for other purposes, we have to remove heat. So that's where, if you look at graphene is a very good conductor of heat. And therefore, if I can make at the back of the wafer, if I can make a channel and I can put graphene into even in the liquid that I use, let's say water, if we use water with the graphene nanoparticles in it, they will have a very high thermal conductivity. They will remove heat. Or if I can even induce boiling on a wafer at the back of the wafer, boiling, as you know, is a very efficient way of heat transfer. If we take a pot of water and we put it on our stove, we see after some time the bubbles start. And that nucleation bubble, those bubbles, they take the heat from the bottom and they bring it to the top. So the whole water gets agitated and it gets hot. So the same thing, I can fix the temperature that I want, boiling temperature. I can say, okay, don't go over 55 degrees Celsius. And I can pick up a fluid which boils at 55. As long as the fluid is there, it's boiling, its temperature is not going to go up. It's two-phase heat transfer, right? So I can use graphene as a nucleating spot. They are small, teeny mini spots, and I can induce boiling on them in the channel at the back of the wafer. So I can use something like that, and I can even use graphene particles in the fluid that I put through it, right? So I have coating of graphene on the surface, which will induce the boiling, and I can have nanofluid with the nanoparticles in it that will also remove heat. So thermal management of data centers. I recently gave a talk at Mahindra University in Hyderabad on thermal management of data centers, which was attended by a lot of people. I know one person from England also attended that, and some folks from IITs. So thermal management of data center is becoming the roadblock for future data centers.
Okay.
How do you remove heat from the chips? Because unfortunately, on a chip, you can have hot spots. One is average heat transfer, average amount of heat to be removed from a chip. The other is you can have hot spots. So a spot on the chip can be much higher in temperature, and that's you have to take care of that. So I think the graphene allows us to look at thermal transport or the removal of heat in a different way than before. For example, I'll give the example. If you have a crowded room and if you have so many people in that room and there's one exit door and there's an alarm and you say everybody gets out of the door, well, people are going to bump into each other and they run into this. That's how electrons move. Okay? But if you have graphene particles, right, so there are only few of them, okay, in the whole room. So they immediately rush to the exit door and they run out, right? So that's the ballistic transport. That's called the ballistic transport.
Okay.
So that's much better than the regular way the electrons remove heat by electrons. Typically, these guys remove heat by phonons. So it is much better medium for transferring heat, and that's why its thermal conductivity. If you think about a polymer, it is one watt per meter Kelvin. Okay. If you think of graphene, 5,000 watt per meter Kelvin, right? Even with defects, it's 2,200. Okay, still pretty good. Right? Not only we have to take care of the heat removal from the chip, but also the walls themselves. How can we reduce the solar load so that the air which is within the system, because we need that air also to be at a lower temperature. If you look at the data center where all the chips are there or all the servers are there, we don't want the air to be at 40 degrees Celsius. We
Sure.
typically require it to be at 20 degrees Celsius or 25 degrees Celsius. So how can we reduce thermal load on the building itself when designing it? So, for example, depending on that, India doesn't have to copy the thermal design here. If they are building new data centers, they should build the data centers in a way that depending on where they are located, whether they are in Kashmir or they are in South India, depending on that, they can build specifically target their buildings in a design them in a way that they correspond to the local environment. So reduce the thermal load on the building and then look at the power of graphene for looking at removing the heat from the chip itself.
Got it. Got
So
it.
we can later on, yes, we can go into graphene quantum devices, make using instead of silicon, making graphene. But that's not people have been writing the demise of silicon for a long time, and we are still using silicon.
Got it. Got it. So, sir, how advanced are we in India, at least, when it comes to using graphene in the examples that you mentioned? Are we still at the research phase, or are we at a pilot stage? Where are we at?
That's what I'm really trying to do. We have a center of excellence in emerging materials at Thapar University. It's called Virginia Tech Thapar Center of Excellence in Emerging Materials. And emerging materials, one of the workhorse is coal-derived graphene. So I have transferred the technology from here, from my lab, to it's called Thapar VT Center of Excellence in Emerging Materials. So it's a partner of Virginia Tech in a sense,
Okay.
and I'm the chair professor for that. So we, as long as we are using our process to make graphene for R&D purposes, there is no problem here. We don't have to pay any licensing fee to Virginia Tech. So we have transferred the technology, and now we are scaling it up at Thapar. How do we go from, for example, synthesizing few grams of graphene to kilograms of graphene? Okay. So we could actually, if you look at all the needs of graphene from India at current stage, it's like 250 kilograms. Okay. So I can meet the needs of everybody in the country if I start growing coal to graphene,
Okay.
either at Thapar or now we have done the same thing with Mahindra University in Hyderabad. I've transferred. We have another center, VT, MUVT, Interdisciplinary Advanced Research Center for Transformative Technologies. Okay, it's a big name.
Yeah.
And then we have had Virginia Tech India in Chennai for a long time. So we have had it there and we have scientists there, who are really working in a Bell Labs mode that I want them to work on, where we looked at, when I was hired in Bell Labs, just a side remark, I was told that I worked with Arno Panzias, the guy who got the Nobel Prize in Big Bang Theory. He was my vice president for research. And, when he hired me, he said, "Son, we hire the best people we can, let them do what they do best. But once in a while, we remind them they work for a telecommunication company." But then after a poignant pause, he said, "But if you're not in the top three in what you do among your peers, you don't belong here." So we are trying to do the same thing at VT India in Chennai. where we have a very select group of students who are research scientists. And so we have transferred this technology, coal to graphene, to them also. So we have at least three places, and we are transferring the technology to Punjab Engineering College, Chandigarh also. Okay. So my objective in answer to your question is coal to graphene will become commercialized soon. And we are scaling it up. We are looking at how do you go from three 3 grams to 10 grams. We already have 30 grams, and then 3 kilogram, then 300 kilograms, right? Or 100 kilograms. And to that end, we will have to get some industry involved with us, people who are very good at scaling up. That's not what academia does. Academia are good at making something,
Okay.
but they're pretty lousy actually when it comes to making them on a large scale, right? So
Yeah.
we are going to line up with some companies. Otherwise, we'll start our own company at VT India in IIT Research Park, and we'll see, wherever it happens, but we'll commercialize it. And so the answer to your question is that day is not too far off. But right now, if anybody wants it, even in Thapur or at Mahindra, they get graphene from our facility there, and they can at least look at for different applications.
Got it.
So they can will provide the graphene to them free. Graphene oxide is free because we make it ourselves. So for
Okay.
our R&D purposes, whether it's to clean water like in Mahindra University, they are looking at the use of graphene for cleaning water, okay, in the river water. Or
Okay.
we are looking at graphene quantum dots for hydroponic growth of plants. How can you, for example, in the plant itself, you can drop a quantum dot, which is a few nanometers in diameter, and it's a carrier. It carries whatever the anti-fungus thing you want to put on it, and it just goes there and deposits there, and you can grow your own plant, right? Or
Got it.
we can use it for taking, for example, the dye from the wastewater in industry. So we are working on that in VT India. How do we take quantum dots or carbon dots, and how can we use them for different applications? So we are looking at different applications in VT India, in 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 Chennai, Mahindra University in Hyderabad, Thapar University in Patiala, and in Chandigarh we'll be looking at that. So once we have a subset of applications that we think India can be number one, number two, number three, and the top three in the world for that particular application, then that becomes a our we are just like Taiwan is in making chips. We are not in making chips, but we are in the downstream. We will take these carbon coal derived graphene, and we have three different sources precursors. Okay, and then by the way, down the road, we can take a rice husk, we can make wheat husk, and make graphene from that. Okay.
All
Not
right.
only from coal, but we
Cool.
can make
Okay.
it from agriculture waste, and then use the same graphene to take care of all the pesticide that we use for making pesticide. We make pesticide. We use pesticide, right? And
Got it.
then in Europe, you can't sell some of the grapefruit, some of the table grapes and all that without, if there's any trace of pesticide, you can't sell it.
Mhm.
So what do? They use a lot of water. Okay, and then they said remove pesticide so that not even a trace amount is left. Now, what do you do with that water, which is laced with pesticide? Well, we can use coal-derived graphene oxide, and that
Okay.
can at least remove pesticide from it. Right. So I think there are a lot of. So we will pick up a few applications in which India should become the powerhouse. And they will say, okay, well, maybe in thermal management or data centers, maybe in taking care of all the pollutants in water, whether it's arsenic or it's mercury. So we are doing that work, for example, in Mahindra University. So we
Got
can
it.
functionalize our graphene. This is the beauty of it. We can functionalize it in a way that it will go and attack one particular arsenic. Okay, we'll give you a material which you can functionalize it to remove arsenic. Mercury, okay, remove mercury.
Got it.
Pesticide, remove pesticide. So that's beautiful. That's why it's called the next wonder material.
Got it, sir. So, and just from my understanding, so this technology that you mentioned from coal to graphene, is that something that is also being researched by other companies and say across the globe? Or is this
Well,
like your
the,
proprietary
well, this
tech in
process
this?
is our proprietary process. This is our patented process.
Okay.
And but a lot of people have worked on coal, but they unfortunately, as far as I'm concerned,
Yeah.
they try to use the same method that they use for graphite. Lot of acids, lot of potassium permanganate, and all that. So our process is called one part process, very simple process. We use only one stupid oxide, one acid, and then we make it into graphene oxide. Graphene oxide itself has a lot of antibacterial properties. To give you last thing on this one, I'm get excited about this. Graphene oxide is hydrophilic, which means it likes water.
That's-
But graphene by itself is hydrophobic. It doesn't like water. Okay. So I can exploit the properties of this. I can make super hydrophobic surfaces. So imagine a heat exchanger for heat removing all kinds of making power plant. In power plants everywhere we use the heat exchangers. So imagine a pipe, and I coat it with hydrophobic material, say graphene. Water is not going to touch it.
Okay.
Water goes through it without touching the walls. No pressure drop, no friction. Right? You can't even have the water go through it unless you give it a little tilt. If you don't give it a tilt, suppose you have perfectly horizontal water. Say, I don't know, I have no pressure drop. How the heck I flow through it?
Right.
But when it flows through it, it can really, without touching the walls, no friction, no pressure drop. Your pumping power is very, very little, right? So we can save a lot of energy. So the same coal which was used for making energy, right? We can conserve energy by using coal drive graphene. There are a lot of properties, wonderful properties. But
Got it,
so
sir.
in answer to your question, other people all over the world, yes, I think our process. We published our first paper in carbon in 2021. Since then, we have published 15 papers or so, and I think it will catch up. But once we pick one application in which we say this is the dominant application, for which a few applications, which cold drive graphene or graphene oxide is the way to go. And if India can become the powerhouse in that, I would love that.
Perfect, perfect, sir. Just a couple of questions more, which touches upon your professional journey. Uh, I mean, you in Bell Labs. I mean, Bell Labs has helped create some of the most important technologies of the modern era. Now, when you compare that period with today's innovation ecosystem, what, according to you, has changed, and what do you think we have lost along the way?
Well, what we have, I can tell you what we have lost in US, right? I mean, I was in the pre-divestiture Mom Bell, where we produced 11 Nobel Prize winners, right? How many countries have produced 11 Nobel Prize winners, right? Just one Bell Labs. We produced 11 Nobel Prize winner before divestiture. Okay. And I was fortunate to become a Bell Labs fellow, which was an honor. Typically you go from member technical staff to distinguished member technical staff to Bell Labs fellow. I went from member technical staff to Bell Labs fellow straight in a relatively short period of time. So there, as I mentioned earlier, the motto was, you do the best you can, we let you do what you do best. And once in a while, remember, you work for a telecommunication company. But the idea was we were allowed to, if something unusual happened, we didn't consider that as a dog. If it's a data point and one data point is outside the linear, let's say it's supposed to be linear relationship, and one data point is sitting there, it's not a dog. We have to explore what the heck that is. Maybe that's the next invention. So Black Swan innovation, it was not formally introduced in Bell Labs at that time. But I used to, as a fellow, I had the privilege of getting a lot of top-notch people in the world in this area. And I'll ask them, what will make you unemployable in 7 years? Their response used to be, of course, we are experts, right? We are never going to be
Never gonna
unemployed.
work.
I said, no, no, no. Technology is moving very fast. What will make you that? So I started to do the same thing at Virginia Tech in my institute. We had what is called Cafe X, coffee shop for the unknown.
Okay.
Okay. So we will invite the more expert in the professor and I'll ask the same, what will make you unemployable? I said, no, no, I'm never going, I'm tenured. Okay, okay. I will need to modify my question. What will make you irrelevant
Yeah.
in 5 years? And I changed 7 to 5. I said, what will make you irrelevant? That whatever you're working on will become obsolete. So that gave rise to what I call it black swan innovation. Black swan, as you know from Nassim Taleb, it's an event which happens infrequently, but when it happens, it has a huge impact. Okay. So, for example, in technology, laser, that will be considered a black swan innovation. Internet is a black swan. Actually, iPhone is a black swan innovation. Okay. So I'm trying to promote in India, in terms of what we can do in India. We have very inventive people. Our kids, if you look at the number of neurons running in their brain, they're pretty large. Okay. And they are the next generation of Indians compared to when I was there. We ask questions. They are not afraid of asking you questions. Okay. And it is those questions that they ask, and more unbiased they are more, if we haven't trained them too much before they become graduate students, first year students are the greatest. They will ask you any question that comes to their mind, right? So it is out of those questions sometimes that you think of the black swan innovative solution. Why does it happen anyway? Why does it happen? Why are you doing this? Why are you not doing that way? Why are you using lignite? Why are you not using semi-anthracite? Okay, they will ask those questions. And you have to think about this. Oh, yeah, it has a calcium. It has, look at the impurities. Impurities are our friends. Okay. And we can also, by the way, from coal, we can also capture a few rare earth elements. Okay.
Okay.
Which
Yeah.
are absolutely used for different applications. So, for example, in at VT India, we are looking on. She came from IIT Bombay, and so we are looking at electric vehicles. So now we are looking only at those rare earth elements, for example, magnets, which will be used for those particular magnets for EVs. So again, our focus is on application, specific application. And for that, hey, okay, this rare earth element, I'm making graphene, wonder material. In the process, can I capture this? It's free. Right? So it's not totally free once you have to spend some money to release
Yeah.
it, to capture it. But still, at least we know for each precursor what are the impurities, are there rare earth elements, which rare earth element we can get it from there. So we have lost that spirit in general all over the world. We have become more focused on, see, politicians worry about, sorry about saying this, but they worry about the next election, right? At the most. And here congresspersons go every 2 years, right? So they basically say constant election time. Then the CEOs worry about the next quarter profit or this 6 months. So where are we going to look at this black swan innovating material technology? How come we in the United States we come up with the Microsoft and we come up with all these the transistor and you name it? How come we don't have that when we have so much brain power in India, right? And I think we need to introduce the culture of excellence. We need to introduce the culture of innovation. Allow our kids to ask questions which are uncomfortable. Allow them to ask, why does it happen? What is it for? Okay, why this way? So I think we want to create both at Thapar and at Mahindra University and VT India, we are creating black swan innovation culture. So we allow our scientists, for example, in VT India, I tell them 10% to 20% of your time, half a day to one day, you just think, come together. Team science equal to big science. Okay. Don't tell me that you are going to come up with a new, those days are gone when you can come up with a new theory or the new material. You work together, and they half a day at least per week they are allowed to discuss something which is out of the box thinking. Okay. So we have lost it, but fortunately in India, when I look at the next generation compared to when I was there, kids are asking questions. They are unafraid. They are not that much worried about the next job in engineering or medicine or whatever. There still are parents are probably, but the kids ask all kinds of questions. So that's the big hope is that our innovation ecosystem ecosystem in innovation will improve because of our next generation of kids who are really asking very wonderful questions.
Got it.
So, yes, we have lost it, but we have also gained it. Okay. We have lost it here because of the focus on elections and the CEO focus on benefits. But at the same time, uh, kids seem to be much more inquisitive than before. So I'm pretty optimistic. I'm a diehard optimist.
That's great, sir. So, but just for my understanding, don't you think when we're focusing more on research, like the black swan concept also that you spoke about, all these would involve a lot of cost and capital too, right? I mean, you have to be investing a lot for them to experiment or research on. Do you think that's ever been a blockage?
Well, I don't know. My time, we didn't even have the equipment, but now I really think that, especially in the universities I'm dealing with, the amount of money, we are not going to make wafer fabs. Okay, they're very expensive. Okay, but there's enough. For example, this stupid coal-to-graphene is a very cheap process, right? We can make it. It's not a difficult thing to do. But in terms of black swan innovation, the creating that innovation culture, it really doesn't require a whole lot of. We don't need expensive stuff. We do need. You are right in the sense that we need all kinds of nanoscale characterization facility and fabrication facility, transmission electron microscopes, the field emission scanning electron microscope and nano indenter, and all these are expensive. Everybody can't have it. But at the same time, there is government of India. I mean, I just looked at the recent initiative on 2D materials, right? GOI from government of India. It was 525 crore rupees for 5 years. Right? That's a lot of money, right? And we invited Thapar, invited Mahindra University, VT India. We went with this hub and spoke model. So we went with Sirius Pilani. So I think there is not a. I don't think it's a dearth of money in India right now. It is mostly a question of our spirit to be number one, number two, number three in the world in certain areas. We need to have that confidence, have that maturity. We have the brains. We just need to find a way to convert that into curiosity, into black swan innovation culture, where we allow people to take risks. We do not allow our kids to take risks. I gave a talk in China at Tsinghua University, and they had invited me for about innovation. How do you do innovation in the United States? How come you guys are so good at innovating? So I had only one slide, and I said, celebrate failure. Their faces fell down. Said, like, that's not in Chinese culture. We have to face we face saving devices. What do you mean by celebrate failure? I said, I don't mean champagne, but you can at least allow kids to take risks. And for example, in my PhD students, all my PhD students, in the appendix, they have to mention what didn't work. Okay. Not only, oh, I did this, I was able to get this process. But I'm sure, you can't say it's intuitively obvious after 6 months of logging. So you put in what didn't work. I wouldn't want my next student to make the same mistake, number one. Number two, we learn a lot from our failures. Just like defect engineering, we human beings are, we are not divine. We are human beings. We have defects, right? But those are the ones which make us lovely.
Yeah.
It is
It's more
the
of embrace it and
yeah, it is that part. You just imagine the cultural richness in India. You go from one state to another, and you find
yeah,
everything changes, right?
true.
So it's the beauty in diversity, and that comes through our individualism. So, in answer to your question, I think I'm pretty optimistic. I'm not. The expensive part is there, but now a lot of universities are getting those instruments also. And on the other hand, at Government of India, at some of the institutes in Pilani, for example, they have every possible instrument that you can think of. You can send it to them; they'll characterize it for you. And but so I don't think the money is the major issue. The major issue in my mind is the cultural shift in the sense of allowing risks, taking risks, allowing failure. Failure is a road to success. We need to inculcate that culture that we don't have everybody go into, for example, computer science at one time and now into AI in one another time. We wherever is the talent, wherever they want to prosper, they want to excel in what you do, and once in a, and happiness will come there, right? Okay, remember Emerson said that proceed in the direction of your dreams and you come across unprecedented happiness. You don't have to get to the other side of the journey itself becomes very enjoyable, right? So I think if we allow our kids to take risks, to and that, of course, I don't want to. I hear this many a time that in India we don't have these. Everybody cannot get a job and all that stuff. But I think if you look at people who really are who really change the society, those are not the people who follow the conventional paths. Many a time they rebelled against their parents and they did something unique, something different. So I think having that mentality, that cultural mindset, and not depending on the everything US is not golden. Okay. And I think we need to have our own strength, our own whatever you want. I don't want to call it egos, but pride in what we already do and pride in what we have. And we are known for jugaad. So we are very innovative, flexible innovation. So given the resources, whatever we have, we still can come up with black swan innovation. With okay, part of the black swan is, oh, you have limited resources. How the heck you do this? We don't have graphite. How do you use coal? Okay, that doesn't require a whole lot of anything else except thinking, right? That we are going to make the problem of having importing graphite, we are going to make that problem as our starting point, and we will solve that problem. We are engineers, for example. I'm an engineer. When we take an oath, we'll say we'll harness the laws of nature to do something useful for society. So I think that mindset has to change. And if we change the mindset in our next generation of young people, and I think they are the prime candidates for that. They have the security. Their parents have provided them, at least in the middle class. They have the security. And if we allow them to do what they excel in, that I think we'll be okay. So I'm not worrying about that. I think we'll be creating a culture slowly and slowly. Once we have the standard of living where everybody at least doesn't have to worry about 2 square meals a day, then I think, we. But there are a lot of people in India now, 500 million or so, who don't have to worry about that. So I may be wrong on these numbers, but there's a large section of middle class families who don't have to worry about it. So let's be optimistic about India. That the world in general. We have 10 grand. Yeah, there are many grand challenges, problem facing the humanity at large. Right, climate change is one of them, and we need to poverty and the democracy and the wars and the pathogens. So if we can focus on solving a problem, and we say we are going to dedicate our mind to do that, we'll do it, and we'll look out, jugaad.
Of course. Sure, sure, sir.
Resource limitation is a nice problem. Okay, we have a problem. Okay, we solve
We'll
it.
figure it out.
Yeah, exactly.
Okay. All right. All right, sir. Thank you. Thank you so much for taking the time. This has truly been very insightful. I have learned quite a lot from this.
This has been a pleasure.